I'm going to do an energy evaluation here, and what we're going to do is get a baseline about what the current amount of electricity and gas that they're currently using, and then we're going to try to bring that way down. And when we bring that way down, how we're going to do that is through sealing and insulating, and which keeps more heat in the winter and keeps more heat out in the summer. And then we're going to take a look at how they produce heating and cooling and see if we can improve those efficiently. And if we can reduce the load, and the load is the consumption of what you're spending on heating and air conditioning, then you'll pay less, you'll save money, and because we're going to insulate and air seal, we're going to improve the comfort dramatically. So you improve comfort, reduce your bills, and then if we do a 0% loan, you can replace your bills. The money you save is going to pay for your loan. So that's a great program. We're going to see what we can help these people accomplish. All right, so I'm going to identify some of the issues that are in the attic that are currently existing and how we can improve on those things. One of the things I'm looking at is the depth of the insulation. So if I measure down here, I know that I'm going to have about anywhere between here, it looks like, I'm going to say 4.5 to 5 inches. It's settled maybe or not. And the rafter is only 5.5, and we're below the rafter. So we know that we have less than 5 inches, right, of insulation. So that pretty much exists everywhere. So when we see the full attic and we look, whenever we could see the rafters sticking up, we know we have something less than 5 inches across the whole room. So we probably have 4 inches, right? Then I look over here and I see that we have no vents. And we also see a lot of dirty insulation. And what dirty insulation means is that we're moving a lot of air through this attic. And by moving air through this attic, that means that we're depositing soil in the insulation. One of the reasons that can be is because of this fan. If they're using this fan as a ventilation system in the spring and in the fall, it's pulling air out of the house and sending it outside, which means that a lot of the dust and things are being kicked up to make this insulation dirty, and it's settling on top. Dirty insulation also indicates some other things, which I'll show you. If they're going to continue to use this fan, it's actually going to be very expensive in the future, because what happens is those fans leak heat out all the time. So my personal recommendation based on energy efficiency is going to be to not use that fan. And actually looking at the belt, my expectation is this is not working anyway, because there's no belt on the pulley and on the motor. So it's probably disabled. So my definite recommendation is to remove this, put up sheetrock and seal it off and get rid of it forever. And they'll stop losing a lot of heat through the louvers of that fan down below. So, you know, that's a recommendation to remove that. So this is an air handler for an air conditioner, which means it's only going to cool. And it was probably added later. My expectation is there's a boiler in the basement, so we're going to go find that out. What you can do with decarbonization is get rid of the boiler altogether and then heat and cool the house with an attic system. That'll be just fine. If you look at the way the ducts are, they're horrible. They need to be sealed desperately. And I'm going to turn the light off and then show you why. If you look closely, we could actually see light coming through the duct system, which means that this system is leaking a lot. Now this is a return. So this return is currently right over here. And you can see the daylight coming through. It's leaking so much air, it's actually pulling some of that air from the attic. In the summertime, this air in the attic space is going to be about 130 degrees. So if you're pulling in air from the attic at 130 degrees, then that goes through your duct system, and your air conditioner has to work harder to cool 130 degrees. And it's actually really only going to lower the temperature by about 15 degrees from the time it enters and the time it leaves. So that means if you're pulling attic air in through all these holes and connections, so we want to seal all this to separate your attic ductwork from the attic and the living space. So that's very important in a system like this. On the supply side also, if we have leakage, it's going to put air conditioning in the attic. You don't live in the attic. So let's look at those. What I want to address here is the fact that in the wintertime, when it's 30 degrees in the attic and 70 degrees in the home, is that on one side of the wall, in a bedroom versus a hallway, it's going to be 70 degrees. On the other side of the wall, it's going to be 70 degrees. So if both sides of the wall are 70 degrees, the theory is you're going to be 70 degrees in between the wall because it's getting heat from each side of the room. However, we've interrupted that because in the attic we have cold air that's 30 degrees, and the cold drops in and then the warm rises up and out into the attic space. So you get this convective loop that allows air that's warm to leave your house and cold air to drop back in. And warm always goes to cold, so it becomes like a big pump that we're pushing the air from inside the house to the outside of the house, because the heat transfers through the wall and rises up out in the middle and comes into your attic. And we don't live in the attic, so I'd prefer to keep the heat in the home. So what I've done is I've moved back some of the insulation so that you can see where the wood meets the sheetrock. And when they built this house, where the wood met the sheetrock was in contact. But what happens after 3 years is that sheetrock stays the same place because it does not shrink, but the wood does, and we get a gap and a separation. So if I put my LED light down in there and I turn off the exterior light, you can see down in the wall. And you know, as you see down in the wall, that shows me that we have a connection between the inner wall and the attic space. So in the wintertime, that connection, and I'll just do this here, which if we put it over this hole, come on. If we go to the other side, you could see even better all the way down inside the wall. Oops. That gap needs to be sealed. So what we're going to do is inject an expandable foam down into that hole and stop the connection between the inner wall and the attic space. Because what happens, see that hole, the wire has a hole there as well. and again here, you know, you could see all the way down in the wall. You can see it's a little harder if I don't have the camera angle correct, but you can see all the way down in the wall. And what happens is in the wintertime, the warm air of your home is going to be 70 degrees and the attic space is going to be 30. So what happens is we get a convective loop. Warm air rises up in the center of the wall and the cold air drops down into the wall and takes heat out of your house. So this natural cycle of convection is going to let heat escape, cold drop in, heat escape, cold drop in, and we want to stop that from happening. This is going to happen everywhere that you have a wall in the attic that has drywall connected to it, which means it's going to happen all the way around the perimeter of the house, as well as in the center of the house by every partition wall between all the rooms. So we want to seal that. That is what air sealing is. That, in addition to sealing your ducts, which means that we're going to stop. You could actually see the hole, the gap between here and the downstairs. So when we stop the connection between the downstairs and the upstairs, we stop the heat from leaving. When we stop the heat from leaving, you don't have to keep reproducing heat. So it becomes more efficient. So air sealing is very, very important. It's probably the least expensive, most rewarding on energy savings. Duct sealing is the next in line for the least expensive and the most deliverance for saving energy, stopping that fan from letting all the heat up here. We're also going to address the attic stairs and stop the heat from leaving downstairs and coming up here. And as I promised before, let's go look at some ducts that are supplies. So here is the supply side, and it's just as bad as the return. And if you look, these are holes that are in the system, which means every time you run your system, you pressurize the duct system and air is forced out into the attic space. I didn't have to go far because this is the very first connection and we find the failure on the first connection. So it's going to be this way everywhere. Another thing I see here is the insulation is not all the way around the metal, which means in the summertime, this is going to sweat. And if we look down below, there it is. All the watermarks from the stains that the system has been sweating because it's not properly insulated. And it's probably making a mark on the ceiling if it reaches the ceiling by the end of the day. And if they're wondering why they have stains on their ceiling, this is why, because this wasn't properly insulated when it was installed. So we definitely want to address that as well. And this whole system is kind of made very poorly. Not kinda, it's definitely made very poorly. And because it's all looped around and swirled all over things and down the other side. And whenever you have all these turns and all these bends, you end up wasting energy because all these turns and bends create resistance, which means there's a resistance to the flow of air. And I'm going to go to the other side of the attic and we'll look at some worse things. All right, so each time this ductwork makes a turn, so we come straight out and we go down, that's 35 equivalent length feet. Then we make another turn, that's another 35 equivalent length feet. We make a third turn. And we go right here in 3 turns, we have 105 equivalent length feet, but really we only have about 5 to 6 feet of ductwork before it goes to the outlet, probably into the bathroom based on where we're located. So because we have so many turns, that means that the resistance of the air to flow through is causing it to take longer to cool or heat the house. So when we look over here and we go all the way down there, that is also a lot of turns that we don't need to make. So the straighter the ducts, the better it is. Now if I look at this one here, we come out, we drape up, we go across, we drape up again, we drape down, swirl around, and there we are. So we have 35, 35, 35, and a little bit more than 35. So, you know, we don't need to go that far to just basically make a short run. It would be better to come straight across and make one turn. So that's what our goal would be, to straighten these ducts out as well. And we can shorten them, which means that by shortening them, we'll have less distance to travel and less exposure to 130-degree attic. So some of the areas I'm also identifying is where there's no insulation at all. Someone has removed it. Here, maybe an electrician, I don't know, but there's no insulation and it's nowhere in sight. Everywhere over there, they put can lights in, they pulled up the insulation. There is another space, another space, another space. I have no idea where the insulation even is in some of these cases. Over there, it looks like there's a leader in the attic, which I don't understand why. But everywhere here, there's can lights everywhere. And each one of these can lights are vented to the attic. Not this one, but all of these are, which means they need to be covered or sealed in some way to stop the air from coming up in the attic and taking the heat with it in the wintertime. So I'm gonna see if I can figure out what these leaders are here for. I have no idea. I have no idea why these downspouts would be in the attic. So I'll find out, maybe not. So as we're investigating, we see the next problem where this is broken off from the air handler from the air conditioning. So if this wasn't addressed, this pan would fill up with water in the summertime and it would probably turn off the system and generate a service call, which is probably not necessary. But if we fix this, then we don't have that problem. Here are some other areas that either have low or no insulation that all needs to be addressed. A lot of areas like that, actually. I'm not sure why it's all missing, but it is. So we want to address all those issues. This is what's known as your combustion appliance zone, and we have fossil fuel appliances that create fire and combustion, obviously, and we want to make sure these don't leak into the home. So this is a atmospheric vent. This is an atmospheric vent, and we want to make sure that before we seal the house, we have plenty of air that feeds these systems, because these systems are going to take the air from the room that you are in to create fire, and we want to make sure they have enough combustion air before and after we start any project. We don't want to cause any damage. Another thing that we're going to notice right away is that in conformance to the code, the vent does not touch or come in contact with combustibles, meaning wood. And if you look, there's a big air gap. An air gap allows air to go from the basement to the attic as the heat rises, or as the heat is cold, it causes the cold air to come back down into this space. So in the wintertime, the 30-degree air is going to come from the attic and drop down into this space, cooling off this space. And in the wintertime, it's also going to allow heat from this space to rise up and go out through the top and go into your attic from the basement. And this is another convective loop that is a connection that we want to stop from happening. Because if we stop the cold air from dropping in and the warm air from rising out, we don't have to keep heating air that is coming from the outside in the basement. All right, so in here, in the laundry area, there's no insulation on the walls. So there's an opportunity to put some insulation on the walls, which would keep this warmer in the winter, cooler in the summer. Up in the top, we have no insulation up here, which is called the rim joist. And there's no insulation in the rim joist all the way around the home. And there are finished walls that were finished before they did not put insulation in the walls. So we have a finished wall for the rest of the basement, but there's no insulation. And of course, there's nothing up here in that space up there. So there's no opportunity to reach it because it's filled with sheetrock. It's covered in sheetrock, and we can't break through the sheetrock to try to do that. So I just measured for carbon monoxide in the atmosphere, and we don't have any carbon monoxide in the atmosphere, which means your combustion appliances, well, it indicates your combustion appliances or have not produced carbon monoxide and discharged them into the basement at the moment that we're here. We're going to do some tests on the combustion appliance zones, and we're going to make sure that these appliances don't spill into the basement and put any vent gases or carbon monoxide out into the house. If we look up here, we can barely see a gap between the wood and the concrete, and that's an opportunity for air to come in through the house. So if we're running the dryer, which just ended, we're always taking air and heat outside, and we're depressurizing this zone. And when we depressurize this zone, air can come in through all these other areas like the rim joist, through this hole up here that goes to the attic, and anywhere that there's going to be a pipe or a connection through the wall, which obviously there's your waste drain pipe, and anywhere that there's a hole and a connection to the outside, when the dryer is running, it's pulling that air into the home from all these holes, leaks, cracks, and connections. So it depressurizes this space. And why we're concerned about depressurizing this space is because we have atmospherically vented appliances. So if the dryer is taking air out of here and it's depressurizing the room, and this appliance, which is burning fossil fuel and letting vent gases go out and escape, as well as this appliance, which is collecting vent gases and allowing it to go outside and escape, if the dryer is running, it can, in theory, depressurize the room so much that it causes the flue gas to come back down into the house. The flue gas carries benzene, it may be carbon monoxide, and a lot of other bad stuff. Benzene and a bunch of chemicals that are being produced by the vent gas actually cause cancer. So that's a health issue and a safety issue. And the same goes through with the hot water heater. So atmospheric needs a certain amount of pressure in order for this to vent properly and leave. And then we have a mechanical device, the dryer, which is artificially depressurizing the room it could pull it back down through the vent and into the living space where the occupants would breathe that toxic fume or unhealthy gas. So this is why we're concerned about everything in the home interacting with one another. So because this is a fairly leaky home, and I know that, when we look at the rim joist, we know that it's not sealed. And because it's not sealed, that means air is coming in through the rim joist. So I'm not expecting this house to be too tight that we can't vent these appliances properly. But it's also going to be very leaky, and we're not going to be able to do anything about it because a lot of this sheetrock has been put up where the rim joist is not accessible, and we only have about 13 linear feet that we can actually put insulation or actually address those issues. So I expect that this house is going to be just fine. We're going to test that now, and we're going to find out. So now I'm going to do a gas test, a gas leakage test. One of the things I'm going to do is open this up so we could start where it begins. And it starts here at the gas valve, and I'm going around slowly to each of the joints where there could be a gas leak. And obviously there's nothing there yet. So far so good. And we want to go slowly around about an inch away and see if we detect any gas. All the way around all these joints. Believe me, if there was a gas leak, this thing would be screaming. So I'm not going too fast. I'm not going too slow. I'm going just right. Sometimes spider webs and dust will get sucked in there. And make sure that's a little dust on that. Now we're only going to do the areas that are accessible because we're not going to tear these people's homes apart. Alright, so it's about as far as we can go. Now we'll check the water heater as well. Okay, try one more place. We can reach. Not really. And that's as much as accessible. So that's all we can do is what's accessible. So now while I'm in the combustion appliance zone, I'm measuring the pressure difference with the reference to the outside versus the input, which is the room. So the difference between the outside temperature, outside pressure right now and the inside is like 0.8, 0.9 pascals. A pascal is 250 inches of water column. I know that's none of that means anything to most people, but it's just a reference point. So the difference between the inside and the outside as far as a reference point is concerned seems to be between 0.6 and 0.9, back and forth. But pressure is changing because of the wind. So what we have now is a negative 0.0, I'm going to say 9 or 0.8, and that's our baseline. So I'm going to start taking that information and then go to the next thing. We have our baseline of pressure in the room, and after a time average, it came out to 0.5 pascals, which is very little. There's somewhat wind outside, which can affect that, but it's 0.5. So we have no fans running, and we're just in natural state of wintertime conditions. Now we're going to go around the house and turn on all the ventilation fans. Then we'll come back and turn on the dryer and anything else that's going to take air out of the house and pull it away from this environment for the combustion appliance zone. Then we're going to test the equipment, the boiler and the water heater, and we're going to test those for drafting correctly under what's called the worst case conditions. And we're going to turn on the air handler in the attic and all of that. So we're going to take as much air away from these appliances as possible and see if they still pass the test and they still vent correctly. All right. I just drilled 2 holes. The first one in the boiler is to measure the vent flue gas and carbon monoxide level if there's any. Then the second hole is to measure the draft to make sure that the vent gas is leaving properly and carrying the toxic waste of the flue gases out of the house and not spilling over into the appliance zone where the occupants live. So this is before we get to this vent hood, which is bringing air in from the room and then helping it assist to draft out. And the same with the water heater. We're going to go and put our tester down inside the water heater where it's just flue gas to measure carbon monoxide. And then we're going to test over here for the draft to make sure that we have enough to vent all the toxic gases out of the home and not into the room. It doesn't spill into the room where all the occupants are. So before we test these appliances, we're going to put the house in what's called worst case conditions, which means when all the doors and windows are sealed as if it was the winter time. And then we're going to turn on all the fans that can withdraw air from the home and compete with the proper ventilation of these devices. And we're going to make sure these devices don't spill toxic flue gas into the home while all the doors and windows are closed and all the fans are on in the wintertime, because that would be unhealthy for the occupants. So the first thing I'm going to do is mark the setting that the homeowner has, which is A, and that's where they have their water heater set. Then I'm going to turn it up to make hot water. The system is firing, and now that it's firing, I'm going to quickly put my hand here to measure to see if it's spilling. So far it's not. And then as a reference to see if it's spilling, if it was, you would see fog on this foil, and I don't see any fog. So right now the flame is running. I don't feel a spillage. I don't see any sign of a spillage. So that's good, which means it's atmospherically venting and it's not competing with the dryer and the air handler upstairs to pull the flue gas back downstairs. So no spillage at initial start. The safety allowance would actually give us 5 minutes for spillage if that was going to happen, but we aren't even spilling from the beginning, so I'm not really worried about that. The next thing I'm going to do is let this appliance run for about 5 minutes, and after I let it run for 5 minutes, I'm going to take a probe and put it down inside the tube, and I'm going to measure whether or not it's producing carbon monoxide. So far no spillage, that's very good. And now I'm measuring carbon monoxide, which, looking at my watch, it's 11:41. Just let it go for a few minutes. All right, so we have only 1 part per million of carbon monoxide, back to 0, which is great. We don't even consider any issues at all until we get over 25, and then we don't get concerned until we get over 100. So right now we're producing 0. There's no spillage. So this device is safe even when it's competing with the ventilated appliances. And then as a reference, I'm just going to give you a flue gas temperature. Typically, this is flue gas temperature is going to be between 350 and 500 degrees. And let's see, we're over 500 degrees. So if the flame burns at 1,100 degrees and we lose 500 degrees up through the chimney, we're losing nearly half of all the heat that that flame is producing. So this is a very inefficient way to heat hot water. There are more efficient ways to do that. You're wasting a lot of fuel. So even though it's a 0.5 efficient system, and we can get down to steady state efficiency, we're losing a lot of heat up the chimney. So there are better ways to heat hot water. So we might as well check the draft pressure while we're here. Right now we have zero difference between the pressure inside and the pressure outside. But as soon as we put this probe inside, we'll check the draft pressure. And we have, looks like negative 8.5, negative 8.1. That's a great draft pressure. Anything over 3 is sufficient. So right now we have negative 8.3. So that's great. So we're fine. We have no problem with venting this appliance. So now I'm checking undiluted flue gas. And the undiluted flue gas is telling me we have 0 parts per million of carbon monoxide. So this appliance is safe. So typically we're between 350 and 500 degrees. So we're almost at 350 now and in flue gas. So when we do our calculations, we can figure out that what the waste is for this unit. So we're at 362, 365. So it's an 84% efficient furnace. So here's what's going to happen. You're going to spend $1 for gas, right? You spend $1 for gas. You're going to lose through efficiency of the equipment 16%.
Right.
So 16 cents of every dollar goes right up the chimney and it never gets burned.
Right.
And the reason that is because it doesn't want to destroy the cast iron heat exchanger.
Gotcha.
Okay. So then the next thing happens is flame burns at 1,100 degrees. And we measured about 350 degrees of temperature, a little 360 somewhere in there. That's 32% loss of heat. So you created fire and lost 16 cents.
Right.
You created heat and you lost
32%
of that heat
right.
up the chimney. And then that means that you kept 52 cents worth of heat to go transfer into the water.
Okay.
So you spend $1 on gas and get 52 cents worth of heat.
Okay.
So that's your ratio. So when we look at other things like heat pumps, you spend $1 for electricity, and then depending on the outdoor temperature, you either get $3.60 at 47 degrees, $2.50 at 17 degrees, or $2 at 5 degrees. I'm sorry, yeah, 5 degrees. Right. So you're still getting a better return. Electric is a lot more money, so it's pretty close to what would be high efficiency equipment. So high efficiency equipment is you're getting a lot more heat retained.
Right.
But in this case, you're using water, which doesn't have a lot of losses. And in the other case, you're using ductwork, which does have a lot of losses in your case.
Right.
So if we seal the ducts upstairs, then we would
Improve.
well, we wouldn't lose it to the attic anymore.
Right.
That means your air conditioning bill comes down in the summer. And if you choose a heat pump, that means that your heating is not going to get lost to the attic space.
Right.
So it's really important that we seal those ducts really well. And also, as I said earlier, we want returns to be in every bedroom where the door is going to be closed. So we definitely want to add returns to those bedrooms.
To those bedrooms.
Right. Because then we're not over-pressurizing the room,
Right.
and we're not forcing it outside through the holes, cracks, and connections.
Right, because that's the only place it's going to go.
Exactly.
Right.
Right. So this is the dynamics of a home. You have to watch where everything's going. See, everyone.
You would think that all this stuff would be.
So when they build a house, the builder builds the cheapest house he can,
Right.
because he knows the market is only so high, right? When he builds that house, every dime he saves goes in his pocket. So that's profit. All right.
Right.
Jen, they also usually underbid things. So when they make a projection and they say it's going to cost 100% to build a house, 2 years down the road when we're actually building the house from the time they applied for the permits, it's 110%. So now he's losing 10% because he didn't anticipate price increases.
Right.
So now how does he have to do it? He has to cut everybody out.
Right.
So he
He's
wants
gonna
to
start-
he wants to squeeze everybody. So he calls the boiler guy, he calls the air conditioning guy, and he says, I know I told you 100%. I need it for 90%.
Right.
Because I gotta, you know,
Yeah, my
that guy's
10% thing is.
yeah, those guys lost money too. And now this guy's going, well, if I got to get the job to keep it, I got to squeeze something out of here.
Right.
How can I cut back?
Right.
And it's like,
This is
there's only two ways to cut back: on labor
our materials.
or materials.
Right.
So if I use less materials, I cut back. If I use labor that's either cheap because it's unskilled,
Right.
they don't know anything and they get junk, and that's what happens. Or if they use labor that's fast and they cut a lot of corners about things that they should be doing that they're not, that's another way to save labor and make money. So this is what happens in construction. Now, and then when homeowners come along, they also don't know about things. Like, first of all, your boiler is oversized for this house. It's probably twice as what you actually need, because it was actually going off on limit for what we were watching before. Means the temperature got hot. So the way a boiler is designed, you're supposed to lose 20 degrees of temperature in the loop. You're not doing that.
We're keeping it.
Right. Well, what ended up happening is you were going out at 180, and then you were coming back at 180. So, and you hadn't reached temperature set point yet. So therefore the system shut down and said, it's too hot. So we're just going to keep circulating until it loses 20 degrees. Then we watched the needle go all the way down. It lost 20 degrees, and
Then it kicked in again.
160, boom, the boiler fired up again. So it's cycling on and off, because the boiler's too big for the house. And there's a lot of reasons why the boilers are too big for the house. One of the reasons the boiler is too big for the house is because years ago, they had 50% efficient boilers. Now you have an 84% efficient boiler. So with a 50% efficient boiler, you've got like 35 cents worth of heat for every dollar you spend.
Right. But now
Right.
with this one, we're getting
Right.
50.
Now you're getting 84 to start, and then by losses up the chimney and everything else, and you're getting 52 cents a dollar on the dollar, right? But when you were losing most of the heat up the chimney, or because they had a bigger boiler, they started with more gas, so somebody sized it for 105,000 BTUs. The next guy that came along, he just assumed
That was what you needed.
if
so-
that was good enough, that'll be good enough for the next guy. And I'm not doing a load calculation. So everything that we do as part of this program is a load calculation to figure out what size you actually need. So if you don't need 105,000 BTUs, maybe you need only 50,000 BTUs, we want to put smaller equipment in.
Right.
In this case, it's a not that old boiler, but they last a long time. They last 25 years.
Yep.
You know, so and you're halfway there. So, you know, but in the case of the heat pump, what you can do is this. So a heat pump is more efficient most of the year anyway, right? So it's definitely more efficient than this. So if you put the heat pump in, and then instead of using this to heat the house, you're using the heat pump, then your efficiency level is going to be greater, and your cost is going to be less, because this has a greater loss. Here you're getting 52 cents on the dollar, where upstairs you might be getting, I can't, like 95 cents on the dollar. So that in the long run is a better deal. It's a better bargain,
Right.
because your total overall bill comes down.
Right.
So on
So
colder days, then this would be the backup.
Well, you don't need any backup with a heat pump.
Okay.
That's an old school, the old heat pumps. The old heat pumps used to stop making heat at 35 degrees, and they needed a backup. The new heat pumps make heat all the way down to 5 degrees, -5, -13 actually now. So you can get heat from -13. You don't need a backup.
So long story short, if we get all the improvements that you're gonna recommend,
Right.
you can get a better heat pump that won't be as big as what we normally have compared to the
Well, you'll
AC
get
we have and this guy.
Everything's going to be smaller. The air conditioning, the heat pump.
Because you
Right.
will seal the house
Right.
better.
Right. When you seal the house, and when you see my video on the ceiling, you'll see the
Saying.
yeah.
Yeah, and we feel it sometimes, because it's like when there are times when I'm like wondering, when we originally got the AC, everything was really nice and cold when it was brand new. And as the years went by, we slowly felt like, all right, I guess this is fine.
Well,
but
if you had a
it's not-
leak, it was slowly leaking out and it was being less efficient,
Right.
which means it probably leaked from the first day that you got it.
Possible. Okay.
So it took a long time for it to leak out, but when it did, you called them back and they said, oh, now we're going to charge you to put some more refrigerant back in because it leaked from the very beginning. And so that's why you saw a degrade in,
Yeah, it's
in
not the house per se.
And
It's
so-
the house didn't change.
Right. Yeah.
Right.
refrigerant.
So the main thing about the heat pump then, if we get this the newer stuff, right?
Right,
is
the
that,
cold
yes,
climate heat
we
pump.
we do have to add more. We
Well,
need more
regardless, you should have returns.
returns, right? We don't
Right.
have a return right now,
You have a central return in the hallway.
right? Which
But-
doesn't make sense, like you said, because
When you close the
when
door-
you close the doors,
There's no return.
there's no return. There's nothing gonna go back in the hallway, right?
Right.
Yeah, because the guys we asked for the heat pump was saying that, yeah, we could keep everything as is, but to be really more efficient, we need more ducts. I guess one of those ducts would be the return that would improve all of that.
Well, you see, there's something else that's going on that he's not telling you. All right, so the first thing that's going on is they don't do insulation and they don't do air sealing.
Nah, they just replace what? Yeah,
Replace something.
And
Right.
add some duct, add a duct or something.
Right.
yeah, but that
So-
has nothing to do with, like you said,
Right.
you know, if with these improvements in general, this would basically get us better.
You remove a variable from the equation.
Exactly.
That's actually a negative.
Right.
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 It's not going to improve anything. All it's going to do is have
Replace
you.
what's there.
Right. So there's the other byproduct of what I'm going to tell you now. So the other byproduct is if you seal and you insulate and then you seal your ducts, guess what you need? A smaller system. So you need a smaller system now. So that means the ducts that are sized the way they are right now will be okay. You still want to put those returns in.
Right.
Because you need that air to come back.
Circulate anyway.
Right, because we don't want to draw any attic air into your system on the return side, and we don't want to lose any air to the attic on the supply side.
Right.
We want to make sure that it's all balanced and it's only exchanging the home air inside.
Not from the 130-degree attic.
Right, in the summer and then 30 degrees in the winter.
Okay.
Right. So that's why we're a lot different than everybody else. Our stuff is very, very, very time consuming and tedious. So it takes a lot of effort to do it. And the business model for most air conditioning and heating contractors is go in, swap it out, get out, and go to the next one.
Right.
And that's all anybody wants to do. So they aren't taking the time to do the load calculation that I always do. They aren't taking the time to say, well, what's your real problem that I always do? So you talked about the room over the garage. You said that they're hot in the summer
Yep.
and probably cold in the winter.
Yeah.
All right? So one of the things I identified is the fact that there's no insulation around the rim joist. My expectation, do we have that light still here or did you put that outside?
It's outside.
All right, so if we go in the garage for a second.
Oh, sure.
Insulation. If you have a phone, you could just point it up there and look anywhere like here or something. In between.
Yeah, there's like it's a hole, right?
You see-
I literally see
Giant
the floor
Right.
of the roof.
Right. So there's no insulation in between here and the room above. So that means it's freezing in the wintertime and it's going to be hot in the summer. Because in the summer this is considered outside because there's not any insulation on the walls over there.
Right, because that's the actual
Right. And there's nothing here.
And this is
Right. And that's not doing anything anyway. Plus this is intentionally loose, although you put a gasket on it. All right. So the reason that is because when you pull a car in the garage, there's the exhaust fumes and there's gasoline in the engine.
right. You want
So if there's a gasoline leak and the fumes leak into the space and they go in the floor, they go in the house, and that's unhealthy. So one of the things that we have to do is we have to seal this along the bottom, and it's best to seal any holes. So in this case, what I want to do is I want a dense pack insulation in your ceiling. When you do that, that'll stop the air movement through the floor. It'll insulate the floor at the same time, and it will make like this environment, first of all, her environment a lot better. And anyone, because you're going to be part of that environment too, because that half is going to be the office.
Yep. Pretty much like that.
Right, so that's going to get warmer in the winter and cooler in the summer. And we're going to stop the airflow that can go through the
Through the
floors
floors.
anymore.
Right.
Because all of this is going to be dense pack insulation. And guess what else happens?
Mm-hmm.
You need a smaller system.
Again, it goes back to the
Right.
entire thing. Right.
So the more we do to save energy by changing the structure of the house, the better you are,
Right.
because you don't need as much heat. So I'm going to create a thermos bottle,
Gotcha.
right? So it stays at temperature for a
everything's
long
all-
time.
Right.
Right. And the number one most effective thing is air sealing, because that stops the heat from leaving in the winter, and it stops the heat or
The cold.
the moisture and air to come in the summer. Because in the summer it's reversed. It's 85 outside, we want 75 inside.
Right.
Right? So now it's going the other way. So hot always goes to cold.
Yep.
So in the winter it's 70 degrees in the house, it's 30 degrees outside, so the heat's leaving. In the summertime it's 85 degrees outside, it's 75 inside, so the heat's coming in. And when the heat comes in, it brings moisture with it. And then you get that sticky feeling, right? We don't want that. So, but now by sealing this, adding insulation and dense packing is the important part. We pressurize the insulation so that it squeezes in as tight as you can,
Right.
because then we don't get air movement through it. And if we don't get air movement through it, we just sealed the floor and the house. So that's good, So now it's just a better way of doing it.
How
And that's-
exactly will that be done? Do you remove the
3.5 pounds per square inch, not that it means anything to you.
Right.
And
Enough
we-
to get it to wherever it needs to
Spread
get
and-
to.
Yeah,
Right.
right. Well, what we do is we push the hose all the way to that side. All right, so let's say we start over here. We put all the holes on this side. Then we push the hose all the way to that side.
Right.
And then we keep pulling it back when
As
it
it
stops.
fills-
filling?
I just feels that.
Once it
right.
reaches maximum pressure, it'll stop going in. So we pull it back another foot
Let
at
it
maximum.
Fill that up.
You just keep pulling it back until everything in there is squeezed in and it's tight as a brick.
So with me with the hole here, what are you gonna do for this?
It's going to make a little bit of dust.
But I mean,
But-
is that a concern that there's a hole?
No, we
here
can
and-
spackle that when we're done.
Oh, okay. So
Yeah.
you're gonna do something.
Yeah,
Okay,
because
okay.
I don't want stuff falling out of the ceiling forever.
Right. Or, yeah. Or
Yeah.
else then it
Right.
circumvents what you try to do. Try to
Yeah.
keep this all packed in.
Yeah, so we can spackle that and then seal it. And then each one of these holes has a plug that goes in, and then that gets spackled.
Right.
And then-
and that's your maintenance tube if ever there's anything that needs to be done.
No, you won't have to do anything.
Nothing.
No,
Okay.
because it's finished. That's it for a lifetime.
Oh,
And
really?
yeah, that's it.
Oh,
So
all
you're
right.
all done. So yeah, that's what's going on.
Okay.
And and you say like, why don't people do this before? Well, number one, that years ago they didn't understand it, and then now they understand it, but they're not doing it because they want to make money, and because the public in general doesn't understand it, no one's asking for it. Right? If you didn't know what AI was, you wouldn't be looking for it.
Yep.
Right? You wouldn't be wondering how to use it because you didn't know it existed. Right? So everyone wants to know now.
It's an interesting way you're doing this because I had years ago when I was thinking of getting my roof replaced, one of the guys said, "Oh yeah, we also do insulation and whatnot." And basically, all he pitched to me was that, "Oh yeah, this entire roof needs to be insulated," and that was it, right? He's not doing what you're doing, when you're trying to understand exactly where all the places are where we lose.
Right. And actually,
Stuff.
insulating the roof is not necessarily a good idea.
Oh, okay.
Well, because you have vents on either side of the house.
Yeah.
And those vents allow air to come in.
Right.
All right. So that's 30-degree air. So if you insulate this and the roof, right? And then you have another insulation on the ceiling, and you have air vent coming in between, you've accomplished nothing. So there's
There's no point.
no point. The only benefit that it can have at all is going to be if you are going to not be as hot in the summer. So because it's not an enclosed space, because it's ventilated.
Right.
So whenever air can bypass insulation, the insulation value is 0.
Interesting.
Yeah.
Yeah, that's interesting. Yeah, and I bet you that person was just telling me because at that point in time, those ventilation weren't there. They were just
okay.
added by the guys, the roof guys, when they said this is the way this is done now. You need ventilation to circulate
Right.
there.
You do need ventilation.
Yeah.
Right.
I bet you that guy was just, well, keeping everything as is when everything was sealed. And he was thinking, we'll just put stuff there and that should be the end of it.
Well, actually, it's never actually sealed. And I don't like insulating roof decks for homes that are already built. And the big reason for that is because all your eaves along the edge are supposed to be ventilated.
Okay.
Right.
I gotcha.
And because in the summertime, it's going to be 130 degrees up there.
Right.
And we want that heat to escape.
Yeah, you don't want it kept in there because
Right.
you're just...
So if you insulated the roof, it would slow down the absorption of heat through that space. But the other thing is it adds square footage to your home that you don't live in. You don't live in the attic.
Really?
Right, because now your conditioned space just went up by the amount.
You just put insulation. Oh, really?
Right.
I didn't realize
But if you insulate the flat deck, like where you are right now,
right.
then what happens is you keep the same square footage that you're trying to heat, and that's it. You're done. So that's why I want to seal the ceiling, and then I want to add insulation to the ceiling, so we don't change the volume of air we have to heat. Why? Because you don't live there. Why do we want to heat that space? There's no value to that.
Sounds like any kids play up there.
Not like anybody goes up there. So, is there anything up there that you really need to have or keep, or?
No, I mean,
Because you have some stuff up there in
that's
storage,
just-
but it looks like
that's
cribs
it.
from
Yeah.
when your children were babies.
Exactly. That's all that is.
Okay.
Yeah.
Okay. So you could take that out and either
Yeah.
donate it or find a home, or.
Pretty much, yeah.
Okay.
I'm keeping the crib, but everything else. Because
Okay. All right, but you could put the crib somewhere else other than the attic?
Yeah.
Okay. Because it's really getting destroyed up there anyway.
Yeah.
Because it's in 130 degrees.
And then it's freezing.
Yeah, it's about equivalent to your shed. So you're putting it in your shed.
I think that's the reason why.
Yeah.
Right. Anything else we need?
Yeah,
here?
no, that's it. We're going to do a blower door test now,
Okay.
and then we're going to measure how leaky your house is,
Okay.
and then we'll have a baseline. Then I take all this data and I put it in a computer.
All right.
But I need the bills too.
Yes, I'll be sending that to you later.
Yeah, just take pictures of I need one full bill,
Yeah.
which has your name, address, and your
Account number.
and all that good stuff on it. So every page. And then on the PSE&G bill, I just need the full page for electric, and when you flip it over, there's a full page for gas.
Yep.
Yeah.
Yeah, I can get that.
Okay.
I got the full bill somewhere in my computer. I just gotta find it and send it over to you.
Okay.
That should be fine.
Okay.
All right.
So now we're doing a blower door on the house, and what we're trying to determine from a blower door is how leaky the house is, because we're taking air artificially out of the house, and if we take air out, we're measuring how much that air is. Because if we know how much air is leaving, we know how much is leaking in, and we're going to locate those areas when we walk around the house in a minute. So we're doing this at what everyone calls 50 pascals of pressure. And in this case, we're measuring about 51.2 because that's what we started with to balance the pressure to zero. It's pretty close, 51.6. And we look over it, and we see 51.7, we get a number of 2817, 2807, 2827. So somewhere around 2800 CFMs are leaking out of the house. So let's go find out where that air leakage is. We could do that by zonal pressure testing, by closing and opening doors to see which rooms are the leakiest. And then we could feel around things like ductwork or windows. And I can tell you 99 out of 100%, it's never the windows. So stop buying windows thinking you're sealing your home. So we're gonna find leaks in like can lights. So let's take a walk around the house. We'll start in the kitchen. The reason I'm starting in the kitchen is because there are a lot of can lights here. So if we put our hand up here, I can actually feel a slight amount of air coming in through the kitchen, all right, through these lights. These lights are connected to the attic, and they need to be sealed because they're currently vented. The heat is vented through the attic. The other area of concern is going to be ductwork. We already know from the beginning of the video that the ducts are leaky. Now the system is off, but I feel a lot of air coming in this duct right now. But the system is off. So why is there air coming in the duct? Because the ducts are leaky and they are not sealed properly. So I'm going to go now, this is a supply, and air is coming in through the supply. Now I'm going to go to the return down the hallway and feel if there's any air coming in there. Oh yeah, I go to the return and there's a lot of air I feel coming in from this space. So that means that the supply and the return are both leaking. They can't both be working in the same direction because this is where air goes up and that's where air comes down, but they're both leaking air because the fan is artificially taking the heat out of the house. So a huge savings is going to be granted here by sealing the ductwork, okay? Now if we do what's called zonal pressure testing, when we put our hand next, well, the door shuts by itself. So look over here at the door and you'll see the door is closing on its own because there's a tremendous amount of air leakage coming in from this room. And if I look in all the rooms, there's really nothing in here because all the windows are closed. So whatever is on that side of the room, in that room, it's leaking to the outside. So that's significant. There's another bedroom here, and as we close this door, yeah, it closes itself as well. So the home, the structure of the house, and there it goes, is very leaky. So there are things that we're going to do because this is a room over a garage and it's essentially not sealed at all and there's no insulation in the floor. So we're going to seal and insulate the floor, which will make this situation better. Other things that can happen are the ductwork, which is most likely is the supplies in these rooms are bringing all this air in from the outside instead of being sealed. That's going to be a huge culprit here. And that's what our blower door is telling us, is how leaky the house is. So if we bring that number down, that means we're going to heat the house less often. And it's obviously going to save energy because we're not going to expend energy to heat the house over and over again. So that concludes our fun for the moment with the blower door. Now I'm going to go back, put together the report, enter all the utility bills. And here we're going to have an answer based on what my training and knowledge is about how to fix this. And I've done hundreds and hundreds of these homes. So I have a lot of experience doing a very good job. So that's how it works.